video, we're going to be looking at describing sets. Okay, in this on this particular frame, we have this. In the years from 1871 through 1884, George Cantor created set theory, which has a profound effect on research and mathematical teaching. Sets and relations between sets are the basis for teaching children the concept of a whole number and the concept of less than, as well as addition, subtraction, multiplication, and multiplication of whole numbers. So here we're going to be looking at what sets are and how to describe those types of sets. Let's start off with some definitions here. A set is any group or collection of objects. A set is just any group or any collection of objects. And those objects that belong to the set are the elements or members of the set. And one method of denoting a set is to simply list the elements inside the braces and label that set with a capital letter. Okay. And then each element of that set is listed only once. The order of the elements is unimportant. And we symbolize that an element belongs to a set using the symbol, and that's the symbol right here, meaning that an element belongs to that set, and the symbol where slash through it means that the element does not belong to that set. And a set must be well defined, meaning we must be able to tell whether or not an object belongs to that set. Okay. And these are just examples of what a set looks like. Usually they're going to be in braces with a capital letter, in this case, and each one of those individual objects are called elements. So here, red, green, yellow, blue, those are objects or members or elements of that particular set. Okay, so here they use the listing method or the roster method. So here, set C consists of the colors red, green, yellow, blue. Capital N represents 1, 2, 3, 4. Notice that these dots are ellipses that continues in the same manner. And by the way, N represents excuse me, it represents the natural numbers. And also L, these are lowercase letters, A, B, C, D, with 3 dots. That means it continues on up to Z. Okay, so these are just examples of how we can describe sets. And this is what we call set builder notation. Okay, and the way we read this is this. The set, E is the set of all elements called X. That's this X right here. This vertical bar means such that X is an element of N. That's how we read this. X is an element of N, or the set of natural numbers, and X is less than 11. That's how we read set builder notation. E is the set of all elements X, such that X is an element of the set of natural numbers called N, and X is less than 11. Okay, now, here we want to write the following sets using set builder notation. Here we got 2, 4, 6, 8, 10, and so on. Now, there are 2 ways that we can write this. By looking at this, we can see that 2, 4, 6, 8, 10 are even numbers. So we can write this in set builder notation as the set of all X, such that X is an even number, even natural number, or you can say the set of all X, such that X is equal to 2 times N, where N is a natural number. Okay, because we take any natural number multiplied by 2, that's going to be in that set. Part B, 1, 3, 5, 7, and it continues on and on and on. Two ways we can write that. They're odd numbers, so we can say that the set of all X, such that X is an odd natural number, or you can say the set of all X, such that X is equal to 2 times the natural number minus 1. and that's less. That means that n is going to be an element of that natural number, of the set of natural numbers. Okay, so that's how we can write sets using set builder notation. Okay, write the set A, which is 2 times k plus 1. That's the set of all 2k plus 1, such that k is equal to 3, 4, 5 by listing its elements. And one way of doing that is creating a table. Okay, so here the k in this column is going to be the numbers 3, 4, and 5. On the right hand side, you get 2 times k plus 1. What that means is you're taking the value of k, multiplying it by 2, and then you're going to add 1 to it. So if k is 3, that means we replace this k with 3, so it'll be 2 times 3, which is 6, plus 1, which will be 7. And then k is 4, replace the k with 4, so it'll be 2 times 4, which is 8, 8 plus 1, which is 9. And then k is 5, so it'll be 2 times 5, that's 10, 10 plus 1, which is 11. So A is going to be these values, 7, 9, and 11, which is this. Okay, next example is write the set B, which is the set of all x, such that x is a positive even number that's less than 8. Okay, in this case, we're writing a positive even number less than 8, which is going to be just 2, 4, and 6. Because those are positive even numbers that are less than 8. So B is just this set, 2, 4, 6. Okay, let's look at some more definitions here. Equal sets. Two sets are equal if and only if they contain the same elements. They have to contain the same elements in order for two sets to be equal. The order of the elements makes no difference. If set A is equal to set B, then that means we write that as A is equal to B. And if A is equal to B, then every element in set A is contained in set B. And every element of set B is contained in set A. And if A is not equal to B, then there is at least one element that is not contained in both sets A and B. So in this case here, let's say that set A had these elements. I'm going to say this C, D, E, and F. And B had this, let's say D, E, C, and F. Okay, those elements are out of order. However, they're both equal because they have the same elements. A and B have the same elements there. That means every element that's in A is contained in set B. Every element in B is contained in A. Now if I added one more, let's say set C was this, A, C, D, E, and F. Here, B and C are not equal to each other. The reason for that is C has an element that's not in B. Here, A is not in set B. Okay? So that's the difference between what equal sets are and what are not equal sets are going to be. And a one-to-one correspondence is another definition. If the elements of sets P and S, for example, can be paired so that for each element of P there is exactly one element of S, and for each element of S there is exactly one element of P. Then the two sets P and S are said to be in a one-to-one correspondence. That's the definition of one-to-one correspondence. Okay? Because one element in P has to be paired with an element in S. Each and every element of one set has to be paired with the other. And here's an example of what one-to-one correspondence is. Set 1, 2, 3 can be placed in a one-to-one correspondence with set ABC by establishing either of the following parents. In this case, 1 can be paired with A, 2 can be paired with B, 3 can be paired with C. And also 3, 2, 1, and then ABC. 3 can be paired with A, 2 can be paired with B, and 1 can be paired with C. But keep in mind, these are not the only possible pairs to establish a one-to-one correspondence. We would like to list all the possibilities. Okay, and one way to illustrate all the possible one-to-one correspondence is to use a table, and another is a tree. As you can see here we use a table here. As you can see, there are 6 possible ways to illustrate a one-to-one correspondence. And if you look at this one, this is what a tree diagram looks like. That's another way of illustrating all the possible one-to-one correspondence. You can see that there are 6 one-to-one correspondences, all the possible ones. How can we determine the number of one-to-one correspondence between 2 sets? In our example, given the element 1 in the first set, there are 3 possible elements in the second set which can be paired with the 1, namely A, B, and C. A, B, or C. Once we have paired an element with 1, that leaves 2 elements in the second set to pair with the number 2. Once we paired an element in the second set with 1 and with 2, there will be 1 element left in the second set to pair with 3. And the fundamental counting principle is this. If event M can occur in M ways, and after it has occurred, event N can occur in N ways, then the event M followed by event N can occur in M times N ways. Okay? So one event can occur M number of ways, and the second one can occur N number of ways. Then event N, M followed by N can occur M times N. And this is where we use the fundamental counting principle. Okay, equivalent sets. 2 sets A and B are equivalent, written A with a squiggly mark, then B, if there exists a one-to-one correspondence between the sets. So if there is a one-to-one correspondence, that means that A and B will be equivalent sets. Recall, if 2 sets are equal, they have the same elements. Okay? We talked about sets A and B earlier. With equal sets, they have the same elements. But now keep in mind, equal sets are equivalent. But not necessarily your equivalent sets are going to be equal. Okay? So let me give you an example of something like that. Let's say sets A and B. Let's say D, E, F, and F, D, E. We know those are equal sets because they have the same elements. Okay? Not only are they equal, they're also equivalent. Because I can get a one-to-one correspondence here. D can be paired with F, E can be paired with D, F can be paired with E. Now suppose I had this situation. Okay. These are equivalent sets. A and B are equivalent because P can be paired with 1, Q can be paired with 2, and R can be paired with 3. Here I have a one-to-one correspondence, so that's an equivalent set. But they're not equal because the elements that are in B are not in A, and the elements in A are not in B. So here, those are not equal sets, but they are equivalent sets. Okay, so that's the difference between an equivalent set and equal set. Here's some examples here. Given sets A, which is PQRS, B, which is ABC, C, which is XYZ, and D, which is BAC. Determine whether the following statements are true or false. In this case here, A is not equivalent to B. Take a look at A and take a look at B. Those are not equivalent because I can't come up with a one-to-one correspondence for those sets. So that's true. Now A is equal to B. Well, guess what? A and B, sets A and sets B do not have the exact same elements. Here A has PQRS, but B has ABC. What's in A is not in B, and what's in B is not in A. So that's false. Here, A is equivalent to C. Take a look at A and C. Well, I can see that they don't have a one-to-one correspondence here. P can be paired with X, Q can be paired with Y, and R can be paired with Z. But S, I can't pair that with anything. So in this case here, that's false. A is equal to C, that's also false, because they don't have this. A and C do not have the exact same elements here. B is equivalent to D, which is true. I can get a one-to-one correspondence for B and D. A can be paired with B, B can be paired with A, D can be paired with, C can be paired with C. B is not equal to D, that's false. Because look at B and D. They have the exact same elements. The order is different, but they have the exact same elements here. So that would be false. C is not equivalent to D. That too is false. Because C and D, I can create a one-to-one correspondence. That means that C and D would be equivalent. So C is not equivalent to D would be false. And C is not equal to D, that would be true. Because in C and D, I don't have the exact same elements. For C, I have XYZ, D, I have BAC. Okay, the cardinal number of a set called S is denoted by N with a capital S in parentheses, indicates the number of elements in the set S. So for each one of these, we're going to find the cardinality of each of the following. Like K has the elements 3, 5, 8, 0, 11. We just count up how many elements are in set K. In this case, it's going to be 5. So here, N of K, or the number of elements in set K, is 5. The second one, L has the set 0. Here, there's only one element, and that's the number 0. So the number of elements in set L is 1. X is the set of all X such that X is a real number and X is equal to X plus 1. That would be 0, because the way this is set up, X has to be equal to the number itself plus 1. That's not going to happen, because if you take X equals 1, you got X equals 1, then you got 1 plus 1, which is 2. 2 is not equal to 1. So N is the number of elements for set X will be 0. And Y, which is the empty set, the circle with a slash is an illustration of what we call the empty set. So the number of elements in Y is 0. Finite sets versus infinite sets. A finite set is this: if its cardinality is 0 or a natural number, that set is finite. A couple of examples are the set of presidents in the United States. Right now we have 44 presidents in the we've had 44 presidents in the United States, so that's a finite number. The set of planets in our solar system, there are 9 planets in our solar system. So that's a finite number. Some might argue that there are 8 planets in the solar system, but I don't know that, but that's still a finite number. Now, an infinite set is a set that is not finite. It goes on and on and on, and you'll know that from one example with the 3 dots. That means this goes on and on without end. That's the set of whole numbers, in this case 0, 1, 2, 3, and it goes on and on and on. The set of solutions to an equation, which will be x plus 1 equals to x plus 1. That represents a finite set. The reason for that is any value of x that you assign and you replace it for x, the left side of the equation will always equal to the right side. So if we let x be 2, that means 2 plus 1 will be 3, and 2 plus 1 on the right side will also be 3. The universal set is defined as the set consisting of all the elements under consideration. And we use the capital letter U to denote the universal set. So the capital letter U is used to denote the universal set. And suppose that the universal set is going to be defined as this. Here, U will be the set of all x such that x is a member of the United States Senate. Okay. Now we denote the universal set with a large rectangle, and particular sets are indicated by geometric figures inside the rectangle. In this case, only members of the U.S. Senate are included in the rectangle. Now this pictorial representation is what we call a Venn diagram. So here you're going to be using Venn diagrams to represent universal sets. Okay, here's an illustration of a rectangle. Now in the upper right hand corner we use the letter U to represent the universal set, and that's your example of a Venn diagram. And then you're going to consider the members of the universal set called U, which are females. Since this set is wholly contained in U but does not contain all the members of U, we denote this set with a circle as follows. Here F is going to be the set of all x such that x is a female U.S. Senator. So here we use a circle and we use the letter F to represent that set of all female U.S. Senators. Okay, consider the members of the universal set, which is U, who are not females. This is the set of all members of the set U that are not in F. Now we refer to this set as the complement of set F, and denoted by the shaded region in the figure below. So here, this green shaded region right here that you see, that represents all the elements that are not in set F. Okay? That's the complement of set F. Okay? So sometimes when you're dealing with, if you take a statistics class, you'll be hearing that terminology of the complement, because you're dealing with all the elements that are not in set F. And that's the shaded area. The complement of set F, we use F with a bar on top, meaning F complement, or the complement of set F. That's the set of all F elements in the universal set called U that are not in F. So, in this case here, F with a bar, complement of F, that's the set of all x, such that x is an element of U and x is not an element of F. Okay? So we're excluding the elements that are not in set F in this illustration here. Okay, look at this example. If U is going to be A, B, C, D, that's a universal set, and B is going to be the element C, D, find B complement, U complement, and the complement of the empty set. Okay, let's look at B complement. B has C, D. Compare that with U. You're going to take out what's in you're going to take out of the universal set what's in set B. Here C and D will be taken out of that set, and you'll be left with just A and B. So B complement has these elements A, B. Okay, U complement, that's the universal set. Take the entire universal set out, you're left with just the empty set, because you're taking all of the elements that are not in the universal set. So that leaves you with the empty set. And the complement of the empty set is the universal set. Okay. And part B, if U is the set of all X such that X is an animal in the zoo, and S is the set of all X such that X is a snake in the zoo, describe S complement, the complement of S. Okay? The universal set has an animal in the zoo. For S complement, you want to take out all the snakes that are not in the zoo. So here we write this as S complement, or the complement of S, is the set of all X such that X is a zoo animal that is not a snake. So you're excluding all the snakes from the universal set. And part C, if U is equal to the set of natural numbers called N, E is 2, 4, 6, 8, and so on, and O is the set of 1, 3, 5, 7, that's the set of odd numbers, find E complement and O complement. Well, E complement is the set of all numbers in the universal set that are not even numbers, so you're just left with just the odd numbers. Because if you take out all the even numbers in the set of natural numbers, you're just left with the odd numbers. And also, with O complement, you're removing from the universal set all of the odd numbers, which means you'll be left with the set of all even numbers. Okay. We're going to talk about subsets. Set B is a subset of set A, which is written B is a subset of A. That's this symbol right here with a line underneath it. B is a subset of A, and that's if and only if every element of B is an element of A. And if set A is not a subset of another set B, it's going to be this. That same symbol, but it's going to be a slash, meaning A is not a subset of B. Okay, let's look at the subsets versus the equality of sets. The definition allows for B to be equal to A. Notice the underscore underneath that symbol. Here, it allows that B is equal to A. If B is a subset of A, then that means this implies that if and only if every element of A is an element of, every element of B is an element of A. Okay? So if A is a subset of B, and B is a subset of A, then we can say that A is equal to B. Okay. Now this phrase if and only if works both ways. If B is a subset of A, then every element of B is an element of A. And the reverse works the same way. If every element of B is an element of A, then B is a subset of A. That's what if and only if means. It's like two separate sentences. Okay, let's talk about proper subsets. Suppose B is a subset of A and B is not equal to A. Then there must be at least one element of A that is not in B. And we say that B is a proper subset of A. And it's written like this. This time you don't have the underscore underneath this symbol here. So we're saying B is a proper subset of A. Because there is at least one element of A that is not in B. Let's look at this. Given that A is equal to the elements 1, 2, 3, 4, 5, set B has the elements 1, 3, P is considered to be the set of all x such that x is equal to 2 to the n minus 1, and n is the set of all natural numbers. Which sets are subsets of each other? All right, now let's take a look at this here. Here, think of this as that 2 to the n minus 1, 2 to the 1 minus 1 will be 1. N is 2, 2 to the second minus 1, that'll give you 3. 2 to the 5 minus 2 to the third, that's 8 minus 1, which is 7. 2 to the 4, which is 16 minus 1, that'll give you 15, and this goes on and on and on, which means that P is going to be 1, 3, 7, 15, and so on. Here, all the elements in set B are in set P. So we can say that B is a subset of P. And also, B is a subset of A. Notice that all the elements in set B are in set A. And A is a subset of itself. B is also a subset of itself. And P is also a subset of itself. Now we want to find out which sets are proper subsets. These are the same sets A, B, and P. Now which ones are proper subsets? In this case here, B is a proper subset of A. Okay, because I can find one element in A that is not in B. Like 2 is not in set B. And also B is a proper subset of P, because only 1 and 3 are in set P. Now I can take an element out of P that's bigger than 3, but it's not in set B. So B will be a proper subset of P, and B is a proper subset of A. Okay, now sets are used in this particular concept of inequalities, and this is an application of set concepts. Suppose A and B are finite sets. If A is equal to B, then the number of elements in A is equal to the number of elements in B, and A and B are equivalent. It is possible to establish a one-to-one correspondence between A and B. If A is a proper subset of B, then the number of elements in A is less than the number of elements in B, and it is not possible to establish a one-to-one correspondence between A and B. So let me go back to this slide here to explain what that means here. Because we already talked about B being a proper subset of A. That means that the number of elements in B is less than the number of elements in A, because I can pull one element out of set A and it's not going to be in set B. Okay? So here we got only 2 elements in B and 5 in A. Since B is a proper subset of A, that means that 2 is less than 5. That's what we mean by how we can illustrate inequalities here. Okay. All right, now suppose A and B are infinite sets. And here we got n being 1, 2, 3, 4, 5, and so on up to n. W, 0, 1, 2, 3, 4, and so on to n minus 1 up to n. W represents a set of whole numbers. Clearly, n is a proper subset of W. How is that? Because 0 is not in set n. There is only one element in set W that is not in n. But it is still possible to establish a one-to-one correspondence between the sets by letting each element in n correspond to the number in W that is 1 smaller. Okay. It is possible to do a one-to-one correspondence. But, in set W, it will have to be 1 less than 1 less. And in this case, n is equivalent to W. Okay, the number of sets of a finite set. If P is equal to, if P has the element A, then P has two subsets, the empty set and the element A. Two subsets, the empty set and A. Now, if Q has the elements A, B, then it has four subsets, the empty set, just A, just B, and then AB. Now let's look at set R with the elements A, B, and C. This time, R will have 8 subsets. One of them is the empty set, the other one is A, then just B, then C, then AB, AC, BC, and then ABC. So, as you can see here, there is going to be a pattern going with this particular situation. Now, if the next set has 4 elements, then that means that there's going to be 16 subsets. So in general, if there are n elements in a set, then 2 to the n subsets can be formed. That's the pattern that you see here, 2 to the power of n. So with 4 elements, meaning that there will be 16 subsets. 5 elements means that there will be 32 subsets that will be formed. Okay, and that's going to conclude this particular video on sets and how to describe sets.